Basic compressor operation corresponds with the ideal cycle pressure-volume diagram. Click on Show Me to compare the two diagrams. When you are finished, click on the right arrow. The work expended in compression is transformed into heat. It is possible to remove only a small portion of this heat, and as a result, the temperature of the gas rises during compression. This increase in temperature causes various parts of the cylinder to heat up to an average value that lies between the temperatures at the beginning and end of compression. In each cycle, there is an area of the cylinder that is not swept by the piston. A volume of gas remains in this area at the end of each compression stroke. This volume is called the cylinder clearance. The cylinder clearance consists of the volume between the cylinder head and the piston at the end of the stroke, the volume between the cylinder walls and the valves, and the volume due to the difference between the diameter of the piston and the diameter of the cylinder. Due to cylinder clearance, a certain amount of gas remains trapped within the cylinder at the end of the compression stroke. This gas is under discharge pressure and temperature. The subsequent suction phase can only begin when this remaining gas has re-expanded to pressure P sub A. The suction valve will not open until this pressure is reached. This causes a reduction in inlet volume. Compression occurs only in the forward stroke. Subdividing the compression work between the two strokes of the crank revolution results in more regular rotational motion for double-acting cylinders. In main and big end bearings, the pin always makes a complete revolution. This allows hydrodynamic lift to take place. In small end bearings, however, the crosshead pin only makes oscillations. The lack of complete rotation makes the conditions less favorable for hydrodynamic lift. All valves used on reciprocating compressors are made up of four basic elements: the valve seat, valve plate, springs, and valve stop. The valve seat is the circular component through which the flow ports are opened. It is sealed by the valve shutter. The seat and valve shutter together mechanically support the pressure differential. The seats are mounted in housings arranged along the body of the cylinder. The valve shutter is the component that alternately opens and shuts the flow ports. The springs are the components that return the valve shutter onto the seat when the flow of gas has stopped. The valve stop or guard is the part against which the valve shutter stops. It determines the degree of lift that the shutter may have. An open structure is used on large frames. The crankcase is U-shaped and allows for the crankshaft to be removed vertically. You can see that the pull of the cylinders tends to open the U-shaped crankcase. To protect from this force, bars must be used to brace the upper part of the crankcase. These bars are called crosspieces. The valve rings are kept lifted by the drag force due to the gas flow. They remain lifted until this force is stronger than the opposing force of the springs. The valve, however, must close just at the end of the stroke, whether it is a suction or discharge valve. If spring stiffness and ring lift or gas velocity are not correctly related to each other, the rings are not stable and will flutter. Springs must be selected so that they are responsive enough to allow the rings to open under the gas force and to avoid vibration. They must also be selected so that they are stiff enough to avoid closure after the dead end of the stroke. If the valve remains open after the dead end of the stroke, closure will happen under both spring force and gas force due to backflow of the gas. The combined effect will result in a heavy impact and likely ring damage. Consider now a single-stage compressor. If a higher delivery pressure happens, the compression ratio is increased and volumetric efficiency decreases. less gas is delivered to the user and the compressor capacity is decreased. The change of absorbed power with the discharge pressure is shown on this graphic. Assume an initially low compression ratio. If the discharge pressure is gradually increased, at first the absorbed power of the compressor increases due to the increase in compression ratio. As the delivery pressure continues to rise, however, the reduction in flow rate affects the power more than the compression ratio. The absorbed power reaches a maximum value and then decreases. Recycle controls capacity by recirculating a portion of the gas from the first stage delivery back to its suction. This system is suitable for multi-stage compressors and works by reducing with the recycle the quantity of gas that is sent to the second stage and beyond. The gas amount recycled around the first stage can be varied continuously. The system therefore is a continuous type control. The first stage handles 100% of the gas under capacity control, but the following stages handle only the reduced flow rate. Therefore, the efficiency of the system is good and increases with the number of stages. First stage recycle is simple and of low cost. Click on the area representing the compression phase. Good, you are correct. Volumetric efficiency is That is incorrect. The correct answer is highlighted. Click on each topic to learn